All right, my little AP Environmental Science disciples, we are going to start on the second half of Chapter 1, which is relatively short, but there are, again, some kind of key themes that will crop up again and again throughout the year. So kind of wrapping our mind around those things early so that we can refer back to them often is our goal here, all right? So, environmental sustainability. Now, we see this word sustainability thrown around pretty often. And, it does have a very well accepted meaning. I just think that it gets tossed out there way too often, all right? And so what we have to understand when we're talking about this environmental sustainability is that here's our accepted definition, all right? So we got to be able to meet our current human need for natural resources, water, soil, food, minerals, etc. Right? We want to be able to meet that need, of course. And like they talked about in the ecological footprint video, we want to be able to do that and live well. All right? Now, the key of sustainability, though, it's not so much that we can't do that. It's understanding that we need to do that without compromising the needs of future generations. So, we need to be able to do this right here, meet the current human need without ecological deficit. All right? And that was kind of that central question that we're watching the video about the ecological footprint. How can we all live well within the renewable footprint? Okay? So can we meet the current human need without an ecological deficit? All right? And so this is the work of environmental scientists. We have to understand, first of all, and really quantify, right, the effects of our actions on the Earth. All right? And of course, we need to get over this notion that the Earth's so big we can never run out of resources. We're already meeting severe constraints, okay? Not even topping off our world's population. All right? So when we say sustainability, we meet our current needs without an ecological deficit. All right? So a couple key things that we notice throughout the globe is this notion of what we call tragedy of the commons. All right? And this was actually brought to the forefront by a man named Garrett Hardin. And what he noticed through his studies is that this environmental issues usually come about as a result of a need to kind of boost one's short-term welfare. All right? And what suffers as a result of this is the actual long-term environmental stability. And so destruction of common or public lands or resources can often result in a private ownership of land. And the reason for that. So let's take a public bathroom, for example. All right? You go to the bathroom at the park or a public restroom or something like that. What do you notice about the cleanliness or quality of that public space? Most of us probably get relatively disgusted by those public restrooms. Now, the reason for that is because it's publicly owned and anybody can access it, there's a tendency in those public or easy-to-access places to use it for your own, but not really take in to your own responsibility list the need to take care of it or clean it. All right? And so the way Hardin kind of defined this problem is it's in these public areas that no one person is really tasked with keeping control of it or managing it or keeping it safe. We tend to see the most destruction in those what we call commons. All right. Now another example, and this one you'll see come up in tests and quizzes and AP tests, is something like the ocean, the open ocean. So countries kind of have their do not fly, do not come in zone. I think it's like 200 miles approximately from their shoreline. Okay, but beyond that, there's this entire just open ocean that is free for anybody to go and travel and navigate and use. All right. Now, because because it is open and free, and there's no one country and no one entity in charge of kind of policing it, managing it, we also tend to notice that we tend to overfish certain stocks of seafood. We tend to just dump sewage from ships or garbage overboard, and as a result, these individual entities are kind of going after their own little short-term welfare. I'm going to catch fish, or I don't want to manage this waste, I'm going to dump it. But that open ocean, as a result, is suffering from some long-term stability issues. Okay, the atmosphere is similar too. People pump all kinds of stuff into the atmosphere, and it gets blown around by atmospheric currents. Nobody is really tasked with managing the entire atmosphere. Different countries have laws in place and so on, but as a result, the atmosphere tends to get diminished over time. And there's some good examples that we'll read and talk about in class. I just want to introduce this idea. All right. So brings us to finally, what do we mean when we say environmental science? And then it turns out there's a pretty broad definition. It's interdisciplinary, and that it encompasses, biology, ecology, geography, chemistry, geology, physics, economics, so, all these different fields. So environmental scientists are really kind of a jack of all trades, but their kind of central focus really is just focusing on, okay, so when humans come in and alter an ecosystem or change something about an ecosystem, how does that end up playing out? We try to map out the impacts of certain little things we do in the environment. And it's worthwhile to map that out because it helps us understand, well, is this practice a sustainable practice? Because we have to, at this day and age, start thinking about, how is this going to affect my children or my grandchildren? How is it going to affect the ability to get food and clean water to this area and so on? And so it's exceedingly complex, and trying to make predictions within this field is very difficult. Okay, so one of the lenses through which we really have to focus is picturing Earth as a system. And so when we say a system, we're talking it's a set of interworking components that interact and function as a whole. And the world's full of systems. So for example, a computer is a system. You've got your different parts. You've got your monitor, keyboard, mouse, your kind of external parts. You've got your internal workings of your CPU and your hard drive and all the electronic components, drivers, etc. that go in there. Those all interact to make a computer work, right? And when we go in and we mess with one of those components, right, it can kind of affect how the whole system works. There can be some sort of a domino, or what we call butterfly effect sometimes. Okay, so when we look at global Earth systems, we're talking about things like climate. Climate is a function of atmospheric composition, right? It's a function of humidity, how much water's in the air. It's determined by the intensity of solar rays, which changes throughout the year and with latitude, right? All these things are interworking components that do kind of interact to a complex whole, all right? And so an ecosystem, when we speak of ecosystem, we're talking about generally the living organisms in a given area, so all the biotic living components, all right, and how they interact with their non-living environment. So we take, the bacteria, the plants, the animals, the fungus, etc., that live in a certain area, all those living things, how do they interact with soil and the water and the sunlight and the minerals, okay? How do those all interact and function as a whole? And now an environmental scientist then would look at the ecosystem in terms of, okay, when we insert humans into this ecosystem, okay, and humans tend to do, behavior X, Y, or Z, how is that insertion of human behavior going to kind of reach its tentacles out and affect that system as a whole? And that's what we call a systems approach to environmental science. It's understanding that systems, particularly ecosystems, are excruciatingly and exceedingly complex systems, all right? And so environmental scientists kind of seek out the interplay between of humans and their ecosystem. We are, of course, living organisms as well, right? And how does the presence of humans affect the functionality of that ecosystem? Okay, that's what they do. And kind of the final layer that we're going to use as starting points for our discussions the next 2 days is this idea of feedbacks. Okay, so when we talk about this principle of dynamic equilibrium, okay, I want you to think, I'm going to talk in terms of your own body, something you're familiar with, right? So your body temperature, for example, hovers around 98.6 degrees Fahrenheit. And I ought to be using centigrade or Celsius since this is a science class, but I don't really remember the actual body temperature in Celsius. Now, that's not to say that your body is staying at 98.6 degrees Fahrenheit. What happens, you fluctuate a little bit, but then your body has responses, all right, within its system to keep it near that 98.6 degrees Fahrenheit, okay? And what those responses are in the anatomy world are often referred to as feedbacks, okay? Usually going to be a negative feedback, okay? And so when we talk about a feedback in science, I know we need to make kind of a mental shift here. When someone gives you feedback on a paper you wrote, that could be positive or negative in that they could be saying good things about what you wrote or not so good things. That's not at all what positive and negative feedback mean in terms of systems, okay? So what we call a feedback essentially is a response, okay? And so we'll say we have a change, okay? So again, going back to this 98.6 degree Fahrenheit, let's say we have a change in the body temperature. So let's say we get a little warm because we're exercising, all right? Now you all know when you guys get a little warm, your body has a response, which is typically going to be activating those sweat glands to put moisture on the outer layer of your skin, all right? So temperature gets above 98.6, your body activates sweat glands, you get some moisture on the surface of your skin. Now, what that does is it causes evaporation, right? Evaporation of water is actually a cooling process of whatever the water is evaporating from, okay? And so what we do is we enact what's called a negative feedback loop, all right? So we increase temperature. That is our change, okay? The response is sweat, okay? Now, this is a negative feedback because it's a bad thing, right? It's not. It's a good thing. This is a negative feedback because the response causes a decrease in temperature. Okay, back to where we started. So what negative feedbacks do is they help us maintain some sort of equilibrium. Okay, so we have an increase in temperature as our initial change. The sweat is our response. The sweat causes the temperature to go back down again, so back to the original state. Okay, that is a negative feedback in a system. All right. Now, a positive feedback would be something where we have a change, okay, and a response. Okay, but what happens as a result of that response is not bringing us back to where we started. What happens in a positive feedback is the response actually brings us farther away from where we started. So we go from a change to a response, and then the response causes a new state. Okay, so the example I put here, like melting polarized. So a change in temperature. So let's say we have an increase in temperature. The response to that in the Arctic would be a decrease in ice. Okay? Now, because we're decreasing our ice, we're actually reducing the reflective capability. And what ends up happening is, so we have a change in temperature of the ocean, that melts some ice. Now, because the ice is gone, the temperature actually absorbs more energy. All all right? And so the temperature ends up increasing even more to a new state, all right? And so the response, rather than bringing us back to our original state, it brings us further away from the original state to a new state, all right? And again, this is another thing that we will talk about in detail, and I'll have you guys draw some graphics and come up with your own examples to really process this. But I just kind of wanted to introduce this, okay? So kind of the key points from this lecture, making sure we know what we mean when we talk about a global commons and tragedy of the commons, all right? Understanding the term sustainability as it applies to environmental science. Understanding what we mean when we say a system and how systems behave with changes in the context of positive and negative feedback. It's kind of the four big ideas in the second half. And over the next 2 days, we'll spend some time really kind of focusing in and processing those, okay? So you guys come in with these notes ready to go, we can start in a really good place tomorrow, all right?